So, you are not so many today, but still it'd be nice if you guys ask questions. I'm going to jump to where I was last week. We stopped at the end of these. So what we talked about last week was inner products, and I think at the end actually there's kind of a summary slide, where we introduced a bunch of things on top of our vector space. So we added first inner product, and then we were able to derive norms from the inner product. So that's called an induced norm, but a norm is just a concept and can be arbitrary. It doesn't need to be induced by the inner product of the space. And then we went on like that. We introduced metrics, and then I said, well, the next step onwards is the topological space. So, so that was it for kind of adding some geometry into vector spaces. The basic idea is that there's, between vectors, we can now have a notion of how close they are. So the notion of inner product is going to tell us some kind of angle between the vectors, and then the notion of metric is going to tell us how close two vectors are. What we talked about last week was vector spaces of function, which is called a function space. And you can easily see that if you have two functions which have the same shape, they will be close, or there's a natural notion of closeness between these functions. Whereas if you have like some weird function like that, and maybe some flat function, then you might say, okay, these two functions seem quite far apart. So that's the notion of geometry. It just comes from this adding the notion of how things are close. And then the notion of topological space, which we will not get into, but just to give you an idea, it's because things have a notion of how close they are, then you can draw a notion of neighborhood between the different vectors or points in the space. And what we will see, though, is the notion of manifold, which is when we have things that are actually not vectors because they don't really satisfy the properties like the, the properties of a vector space, of a group, so that things have to be, what are the properties of a group? Remember from the linear algebra lecture, what are the properties of a group? So how many laws are associated with a group? Yeah. Yeah. So this inclusion property, it's called a closure, which means that if you use that combination law that you have between the elements, the resulting element remains within the group. And you call that inclusion, right? Did you say inclusion or did you say closure? Huh? Oh, you said closure. I mean, inclusion would be a fine word to describe that as well. That's what I heard, but okay. Yes, so identity element, inverse element, closure, and associativity of the, Okay, anyways. So these kind of properties, we add on properties on top, and then eventually, so this is in relationship with vector spaces, but topological spaces do not have to be vector spaces. This is just another type of property. So if vector spaces are topological space, then yeah, sure, but this diagram makes sense, but they don't have to be. Okay, so today we're going to talk about orthogonal projections. And what are those? So the basic intuitive idea of orthogonal projections is something that you've seen in school. So we have some kind of vector here, and by orthogonally projecting the vector y onto the vector x, what we mean is that we go with a straight angle here onto the vector x. And this pi of y would be called the projection of y with respect to x. So that's the intuitive idea for what an orthogonal projection is. So does somebody have an idea what the property of that projection is? What is the property of that point with respect to that point here and that line, you would say, apart from the orthogonality property of the projection? I think the key aspect here is that when we do these kinds of projections, the key aspect is that this is the closest point to this one, because we're going in a straight line onto the line, the blue line. So orthogonal projections have the key property of projecting a point in the closest way to the line. That's the idea. That's the intuition. So projections generally are a class of linear transformations that, other than translations, scaling, rotations, and reflections, translations are somewhat easy and obvious, kind of trivial things, scaling as well. We will see rotation at the end here, hopefully today. And reflection, we will not see that. But anyway, so projections are another type of linear transformations. And we will see how this kind of key intuition that we have here of like projecting orthogonally on a line can go to like the higher dimensional case and so on in the next slides. So in machine learning, they can reduce the dimensionality of a data set by projecting to the most informative dimension. This is something that we saw in the introduction lecture. I think, yeah, we saw how we could, no, we didn't see that. But the fundamental thing in machine learning that you should see, I don't know, how many of you guys did machine learning or are going to take machine learning? So let's say, so only 2 of you, 3. So is that you already had a machine learning, or are you going to take machine learning? You're going to, and you're going to as well. You already had. Okay, so only 1 person had machine learning. Well, so the first lecture on machine learning usually is about linear regression. What linear regression is just like, you can view it simply as some kind of orthogonal projection onto a line. So you have a bunch of data that is scattered, and you want to find a linear model that explains your data. And that's the first lecture that you see on machine learning. And then you move on to all sorts of stuff. Eventually you arrive at neural networks. So linear regression can be interpreted using, this was typo, as performing orthogonal projections. So this is just what I said. So what is the definition of a projection? The key notion here is the idea that if you repeat the projection, any operator that is called a projection, regardless of whether it's an orthogonal projection or not, if you apply the projection after having applied the projection already, then it's just the identity. You're just applying the projection once. So you can apply the projection as long as you can apply that operator as many times as you want, and you don't change, it's a fixed point, then that operator is called a projection. So of course it is the case here. So if I project onto the line and then I reproject onto the line, that point I will arrive at the same point. That's the idea. But yeah, so here we are talking in the context of vector spaces. So we have a vector space V and a subvector space of VU, and a linear mapping. So the projection is a linear operator between V and U. Then it is called a projection if after applying projection, if applying the projection twice leads to the same thing. Of course, and we talked about this in the linear algebra lecture, since projections in this context are linear operator, they can be represented by matrices, and this is what we're going to see in the next slides. But first, we're going to see the 1D case, so the thing that I had on the left part of the slide. So a one-dimensional subspace of Euclidean space, U here of our n, so our n-dimensional Euclidean space, spanned by a single vector taken out of our Euclidean space, expressed in this way. So we are simply scaling a single vector, which we would call a basis vector for our vector space. This kind of space is called a line. And then the question is, how do we project on a line? So this is what we had earlier. Now I did a single thing here, which is saying that the projection onto the line is necessarily a scaling of the basis vector of that vector space. Here, that vector space is one-dimensional. Again, do not confuse the dimensionality of the basis vector with the dimensionality of the vector space itself. So here, the vector space is just one-dimensional. The vector is two-dimensional on the board. So we know, by definition, that our line, our vector space here, is defined in this way. So it's a scaling of the basis vector. So when projecting y, we compute the projection y in U that is close, quote unquote, to y. That means that it's minimizing the distance between the projected point and y itself. And this is kind of where, this is the link between geometry and inner product. It's that the closest point will be the one that is orthogonal to the line. So how can we derive the projection matrix from there? So first, we use that notion of orthogonality. Anything that is going to be, any point that is going to be closest to the line element is going to have an orthogonal a vector pointing between that point and the line. So we say that, we write that down in terms of inner product. So orthogonality being defined by the inner product between the point, so that is the y minus pi uy is this vector, this dotted vector here. So the angle between this dotted vector and the basis vector that composes our one-dimensional vector space is 90 degrees, which means that the inner product here, actually we're just like in 2D geometry, so we're considering the dot product as inner product, is 0. And so we then replace that thing here by lambda x, which is the scaling of our basis vector. So the angle between that vector and that vector is 90 degrees, which means their dot product is 0. So that's the orthogonality property. Second, we use binarity of the inner product. And so that means that bilinearity means that here we have a sum. It's a difference actually, but it's a sum between this and negative this. And so we can decompose the inner product between as a sum of two inner products. So this guy here and this guy here. And this is equal to 0. Then we just do a little bit of high school algebra here. And we obtain that the dot product between the y vector and the inner product between the y vector and the x vector divided by the square norm of the x vector is equal to lambda. So now we have solved for lambda, and because our point is fully specified on the line, is fully specified by lambda and the basis vector x, we now have specified our point. So the last part is, given lambda, how to then specify the point. And it's simply multiplying lambda by x. This is how our one-dimensional manifold is defined. Every point or every vector in the one-dimensional manifold is lambda times x. So that's what we write down here. And then we have a bunch of algebra again. We use the property, so then here we switched to dot products. So we are just doing it for the Euclidean 2D space. Actually, this is a Euclidean ND space, sorry. And yeah, so what we use here is that the dot product is symmetric, so we can switch the order of x or y times x, and we can put the y element here. And then we can identify that we have something that's multiplying y, and that something is the projection matrix. Okay? Are there any questions here? So this should be quite clear, because the next step is just we're going to generalize that to projecting on sub-vector spaces using, higher dimensional things. Is this okay? Like the reasoning? Also, you should really, just as I think I mentioned, like the Penrose pseudo-inverse is something that you just have to memorize at some point. I think this formula you should also memorize. This eventually that's an important result. Like the outer product of the basis vector divided by the squared norm of the vector. This should be known. Okay. So if we take a numerical example, the question would be, what is the projection matrix onto the line through the origin spanned by some vector? Here it's 1 to 2 transpose. Then we just apply the previous result. We just swapped our notation from x to b. And so we have b times b transpose divided by the square norm of b. The square norm of b is just the dot product. So we compute the dot product, and this is 1 plus 4 plus 4. And so that's 9. And so that's what we find here. And then we multiply by the outer product of the b vector. That's a little bit more annoying to compute, but that results in this matrix here. And then we apply it to some vector, like 1, 1, 1. And so we plug our vector here. This is our y vector, by the way, from the previous slide, that we call x now. And then by multiplying this with the projection matrix, what we get is something that is in the span of 1, 2, 2, which is 5, 10, 10. Well, divided by 9, scaled. Okay? Okay, so now the question is, how do we move on to projections onto general subspaces. So we have a vector x that we've called x now, and we want to project it onto some subvector space that is defined, or that has a basis of two vectors. So it's a two-dimensional vector space. And it's a subvector space of R3. And yeah, so this is what the general process looks like. We're going to have the same problem, which is to identify the projection vector, and then identify like the property, which is the orthogonal property with the plane. So the closest point on the plane to the x point here is going to be a point that is that generates this orthogonal projection with respect to the plane. So so the vector space has a lower dimensionality as the kind of as the space that's kind of embedding the vectors. So we have our basis for our subvector space is B1 drawn to Bm. So here we only drew B1 and B2. And what we want to do is find a vector in that subvector space, which means that we want a combination, a linear combination of the basis vectors, which in this case we are in Rn. So we can write down the linear combination of the basis vectors as a matrix multiplying some scaling factor, and that of some scaling vector, okay? So that scaling vector is just a bunch of these lambdas stacked together. And the basis matrix is the expression of the basis vectors as columns of B here. Note that the number of rows of that matrix is n, and the number of columns of that matrix is the number of basis vectors in the subvector space U. Okay? So we can write this down like that because we are reasoning in R n. And yeah, so if we are in a general vector space, like for example the function spaces which we saw last week, we could not write things down like that because the basis vectors are functionals, and they're actually infinite dimensional functions, whatever. So we cannot write them down as a matrix like that. I mean, we can maybe discretize and then end up with something like that, but in the general case, the basis vectors are abstract vectors. So this is coming back to the notion of coordinates, which are some vectors in Rn representing how the basis vectors, which might not be in Rn, are combined. So here in Rn, the coordinates and the vectors themselves are somewhat a little bit the same thing. Okay, so find the closest point in the subspace, and we do that by we define that as the point which is orthogonal to all the basis vectors. So this is what's written here. So we have that for all the vectors in the basis, we have an orthogonal property between the projection vector and the basis vector. Okay, so now we can derive our projection matrix. So projections of a vector x onto so that's what was on the previous slide. It goes like this. So we have the same steps. So the first thing is we say, well, we have similar steps. But the first one is the same. So we are saying we have an orthogonality property, and we derive the matrix here. the way we do that is by stacking the basis vectors. So here we have that each row is a basis vector of our subvector space U. And we have here a vector, yes, a vector which is the difference between the point that we're projecting and the expression of the point that we're looking for, which we're looking for these lambdas. So that's the projected, well, so that's the point once projected, and that's the point that we are projecting, okay? And so that's the result of that. So that's actually the vector between the projection vector. That was this dotted line. Anyway, so okay. So we write that down in just a different form here. So we call that matrix is just B transpose. Remember, so we were composing this big B as just columns of a matrix. So now we have rows of a matrix, so it's just the transpose of it. So that's B transpose times X minus B times the lambda vector is equal to 0. Okay, so now we had this thing of bilinearity, which allowed us to separate the product, separate the inner product in two. So this is kind of like a similar thing. We use distributivity here to have the two sides here, and then we can put them on both sides of the equation. And now we have to solve for that. So what's going to be the result of that? Hmm? So what we want is like lambda is equal to something. Yeah, but so we want lambda is equal to something. So how do you go from B lambda is equal to X to lambda is equal to something? Hmm? Sorry? You invert lambda, beta, B, sorry. The problem is that B, so B is not squared. Sorry, what was the other thing? I don't see who's talking actually with the masks. Oh, you were talking? Yeah. Yeah, so if you said it, so we remove B, and then we somehow get B on the other side, so we cannot do this because it's not invertible, because it's not even squared. So the solution is what they said, so the pseudo-inverse. The idea is that B transpose B, this is always invertible. I mean, always, yeah. And almost always. And so this, we can multiply by the inverse of this on the left side, by the left side. And we have lambda times B transpose B inverse times B transpose X, and this is equal to lambda. So this system of equations that we had here, this is called the normal equations, and it is solved by the pseudo-inverse of B, and that's just what I said. So that result is super important for all sorts of stuff, and especially in machine learning, in data science. So the pseudo-inverse, the idea that the pseudo-inverse of, actually in machine learning, it's the pseudo-inverse of the data matrix, leads to the linear regression. So it's also important in robotics because in inverse kinematics, what we're looking for is if we're trying to move the hand of the robot, the end effector of the robot, what we are looking for is joint angles that minimize the distance to some hand command that we have. And that's also an orthogonal projection there. I don't know, it really, so that's a result that you really need to know. And so this is the solution of something that's called least square problems, because it's I think it's on a different slide. I think it's on the next slide, sorry. Yeah, anyway, so if we want to have then the point, of course, so this is just telling us how to linearly combine the basis vectors in order to recover the projected point. But if we want the projected point, then we need to multiply that by the point itself and multiply that by the basis vectors. So the projection matrix is actually this. That's the pseudo-inverse, and that's the projection matrix. And yeah, so we can write the projection matrix like that. Yeah. And yeah, so so that's if n is equal to 1. We can write it like that. And you can see that here then what we have is the reciprocal of the dot product. But of course, if you have a matrix here, then the reciprocal is there's no reciprocal. It's going to be the inverse of the matrix. Okay. So yeah, so the pseudo-inverse is the solution to least square problems. And there are problems of the form f of x minus y, minimize f of x minus y in the squared norm. So the square norm of f of x minus y. So if you cannot solve for y is equal to f of x, then you try to minimize the square distance between y and f of x, and the solution will be the pseudo-inverse. That's why they're called least squared problems. Okay. So numerical example. Now we have two basis vectors that span U. And we have some points. All these vectors are embedded in three-dimensional space. And we define the kind of basis matrix where we're just stacking our two basis vectors that define our subspace. We compute the product between B transpose and B, which is this small squared matrix here in the middle. And then we multiply X by B transpose. We solve on normal equation here, which we could have gotten by computing the pseudo-inverse. Here we just do it. We don't have to compute the pseudo-inverse, right? We can do it by Gaussian elimination, just the same. We project the vector using the solution times B. And here's the projection matrix, which we compute by inverting B transpose B, where the inverse can also be computed by Gaussian elimination. Remember how we do that? We fill up like the matrix, and then we put on the other side the identity. Okay. So to note about orthogonal projections, the projections lie in a lower dimensional space, and what we're looking for are the coordinates of the vectors with respect to these basis vectors, coordinates we call lambda here. So if we are projecting on general vector spaces, we have to be careful about what kind of inner product we're actually using, and because the angles between vectors depend on our choice of inner product. So, projections allow to solve systems that do not have solutions, systems of linear equations. And how they do that is that the vector B, well, in the case where the vector B does not lie in the span of the columns of A, this is just what I was saying. So if we are trying to solve a system that is f of x is equal to b, or if x is equal to y, whatever, and there's no solution, then we can solve for the least square solution. So the solution that minimizes the kind of distance between the left side of the equation and the right side of the equation. And that is what these pseudo-inverses actually lead to. So we find an approximation solution that is close to solving the equation. And one way to do that is to compute the orthogonal projection onto the column space of A. So the column space is equivalently the basis vectors in which we are trying to find a solution. And these are called least square solutions least squares with respect to the dot product here. And then again, when the basis beta of U is orthonormal, well, so that's just a side note actually. So when it's orthonormal, then the least square solution just we can just have by using B transpose here. Okay, that's all of what I wanted to say for that. There, we are quite late on time. So here, in the couple of slides that remains here, it's an algorithm that allows to transform a random kind of basis for a vector space into an orthogonal basis. This always exists, and the span of that new basis, the basis U here, is the same as the original span of that basis here. And the algorithm that can do that, the Gram-Schmidt algorithm here, what it does is that it orthogonally projects the remaining components of the vector onto the vectors that we have so far considered. So each vector bk is projected orthogonally onto the first vectors, and the projection is subtracted to bk, yielding uk, orthogonal to all the previous basis vectors that we've computed. So the way it works, so just on the 2D example, is that we have originally our basis, which is not orthogonal, which is not orthonormal. So you can see that the two basis vectors don't have the same length and they're not making a right angle. The way we do that is we first project onto, project the first basis vector onto the second basis vector, and then we project the remaining components of the second, is that a typo? Of the second basis vector onto the first basis vector that we obtained. So I'm going to do that with a numerical example. So we have our basis for R2, and these are these two vectors that we have here. And we construct an orthogonal basis in the following way. So first we set the first kind of new basis vector to be B1, which is this guy here. And then we orthogonally project B2, which is this guy here, onto U1, which is B1, because we're just starting the algorithm. It's just the initial phase of the algorithm. But this then would be recursive. Then we'll choose U2 and so on. Okay, so now we have the orthogonal projector, which we've derived. How to project on the line? We derived this initially. So remember that formula. U1 times U1 transpose, so the outer product of U1, and divided by the squared norm of U1. And that gives us U2 here. This gives us U2. Okay? So now we have an orthogonal basis, and we can just normalize that these vectors to get an orthonormal basis. So I guess, so the final thing, which is maybe not apparent here. Oh, the typo is here. So this is not B2. This is not B1. This is B2. So here. Oh yeah. So U2. Sorry. U2 is equal. So U1 is equal to B1. And U2 is equal to B2 minus the projection. So if we remove the orthogonal projection of B2 from B2, what we get is U2, which is this vector that is orthogonal to B1, to B2, sorry, to B1. Confusing with all these indices. Okay, well, that's not so important. It's just to see you to show you an application of using orthogonal projections in the context of coming up with a new basis for an orthogonal basis for a vector space. Another thing we can do is we can do orthogonal projections on affine spaces. Remember, affine spaces are not directly vector spaces. They are a vector space that is kind of offset by another vector. So that's kind of the depiction of that. So we want to project onto an affine space where B1 and B2 are the basis vectors of that subvector space here. So we do that by finding also the orthogonal projection initially to the vector space that is offsetted back in the plane here, and then we will offset the projection that we get. Okay, so that's another application here. All right, so that's it for orthogonal projections. So we saw how to derive the projection matrix for the n-dimensional case. That's like the most important result from that section. And then we saw these two applications. So the Graham-Schmidt algorithm, and then coming up with operating projections on affine spaces. Now we're going to talk about rotations. So rotations are typically also, so they are a class of linear transformations, just like orthogonal projections are, just like translations and scalings and stuff like that. Their key property is that they preserve angle and lengths of vectors. By convention, when we talk about rotation, especially in the plane, we are talking about rotations being positive counterclockwise. So let's see 2D rotation here. So So you've all seen this before. So we have our basis vectors for the plane here. And then we operate a rotation of theta. And what we have here is the linear transformation of the vectors E1 and E2. And we call that linear transformation phi. And then we just identify what are the coordinates of the new basis vectors, of the rotated basis vectors. Okay? So these vectors have coordinates in R2, which are 1, 0, and 0, 1, and they are called the standard basis. The rotation takes as input theta and maps vectors in R2 to vectors in R2 and maintains orthogonality of the vectors, which implies a basis change. And the linear map for the basis vectors is defined in the following way. So these are the coordinates of the rotated E1, and this is the coordinates of the rotated E2. So what this means is that we apply the linear transformation to E1 and to E2, and then we look at the coordinates in the standard basis for these vectors. Okay? So the key thing that's happening here is that we have an automorphism of Euclidean space. Remember what automorphism means? It means that we are mapping vectors from R2 in this case, but from the vector space to the same vector space. And here this vector space is R2. And actually what we are considering is the same basis for the input and the output, the same vector space with the same basis. And that's how we identify these two transform vectors, because we look at the coordinates of these vectors in the same basis, which is defined by E1 and E2. So what we are looking at here is the coordinates of E1 and E2 after rotation in E1 and E2. And from that, we can construct the rotation matrix, because remember, the transformation matrix, I will go back to that in a few slides. The transformation matrix, which is, you could say, the coordinates of any linear transform is a matrix, and it's called a transformation matrix, is the stacking of the columns. So each column are the transformed basis vectors as defined in the output vector space basis. So here it's the same, it's an automorphism. We're going from the same vector space to the same vector space, and we are using the same basis on both sides. So anyway, so that allows us to read the transformation matrix associated with the rotation directly from this figure here. Okay, so that's, I said you have to know the orthogonal matrix definition, which goes through the pseudo-inverse. Same thing, this is one of the key results here. And you need to know like the shape of a rotation matrix, or actually how to rederive it in your head. So in R3, I'm thinking about making a whole lecture on rotations and introducing Lie groups and stuff like that, and quaternions, but I don't know if I will have time to do this. So in three-dimensional cases, we can rotate any two-dimensional plane about one-dimensional axis. So we can construct rotation matrices for each of these axes just in the same exact way by identifying what are the coordinates of the new axis after rotation about one axis. And this is that. And then we can compose rotations by just multiplying the transformation matrices. So I didn't talk about composition of linear maps, but basically composition of linear maps, so meaning applying a linear map after a linear map after a linear map, results in coordinates by just matrix multiplication. So it's the transformation matrix times the transformation matrix and so on. Yeah. So we talked about matrix groups. Matrix groups, then I asked again, so how we define a group. So we have a neutral element, we have an operation which has an inverse, and we have closure and so on. Matrix groups are groups where the elements are matrices, and typically the operation is matrix multiplication. The inverse is matrix inverse. And so the group that we are generally interested by is the group of squared matrices that have an inverse, so whose determinant is not 0. This group is called the general linear group, and it writes like this, GLN. So why I'm talking about this in terms of rotations, it's because, well, so the inner group operations matrix, I said that, so the neutral element is actually the identity matrix, and any square matrix in that group has an inverse element, which is called A inverse. So the interesting part, why we're talking about that here, is because there's a subgroup of the linear group, which is called the orthogonal group, where the inverse of the matrix, of the squared matrix, is a transpose of the matrix itself. That is because the columns are orthogonal, each column is orthogonal to each of the other columns, and orthogonal in the sense of the dot product. And then there's a subset of that orthogonal group where the determinant is -1. And this group represents rotations of our n. And that's the n here. So rotations are a set of linear maps that are represented in coordinates by these matrices, which are these elements of SON, which is some subgroup, and I stated the restrictions here, some subgroup of the general linear group. Okay? So that's all you need to know to kind of get an understanding of what the special orthogonal group is. But of course, there's all sorts of ways to represent, especially in 3D, to represent 3D rotations. You probably have heard of quaternions before, or have heard of the axis angle representation, or the Rodriguez formula, or all that stuff. And yeah, so there's all, and this theory usually has all sorts of connection with SO3. So I might do a lecture, just the whole topic on that. And if I do that, usually it's in the context of Lie groups, because what a Lie group is, and the SO3 is a Lie group. So what a Lie group is putting on top of the group structure a manifold structure. So saying that you can kind of differentiate between the matrices. Because if you can imagine that there's a rotation that does that, and then there's a rotation that does that, plus a tiny rotation on top, you can imagine that you can actually smoothly interpolate between rotations. That's exactly the definition of what a manifold is. And that's a Lie group, actually. So it's a group that is differentiable, basically. So we might talk about that, about SO3 in more detail, how to represent all the different things, and then talk about how the differentiable structure that you can put on top of SO3. Okay, so but so far, because we are still in linear algebra, the key thing, or just like the geometrical properties on top of linear algebra, the key things is that rotations preserve distances, preserve angles, and that 2D rotations are actually commutative, but 3D rotations are not commutative. Be careful here. And the final piece concerns the addition of the vector space of rotations with some translation, and this is called the special Euclidean group. So this is like another, let's say, subset of the general linear group, which is called the special Euclidean group. And the matrices have this shape here. So how many of you have seen this kind of matrix before? I mean, apart from this class? None of you? Are you too? Okay. Okay. So, I mean, so this for everything that's computer vision and robotics, I think apart from that, maybe a little bit in controls. Yeah, probably in controls, okay. But for control, computer vision, and robotics, like this is like super important. So it's the special Euclidean group is basically the group of affine transforms where you're representing your vectors in homogeneous coordinates. That means that you have, so it's the group, so if you're in 3D, why is it super important? Because if I have a rigid object and I'm in 3D and I want to represent how that object can move in space, it's rigid. Okay, so its parts are not moving, and I want to specify the state of that thing, how it moves. So it can translate, and at the same time it can rotate. That's the properties of a rigid object. Well, its state is fully represented by elements of that group, of that special Euclidean group, and they can be represented by these matrices where you have a corner of it is a rotation orthogonal matrix, and then you have a little vector that is the translation associated to the state. So one thing specifies the position, the other specifies the orientation, or equivalently, like how it rotates or how it moves, like translates. So R is a component of the special orthogonal group, and V is a component of Rn. So yeah, it's a subset of the affine group because here we specify that this has to be part of the special orthogonal group. In the affine group, this matrix here is arbitrary. And the affine group is a superset, subset, I think, of the general linear group. Maybe I have to check that out. Superset? Yeah. So yeah, so elements of SEN are called rigid motions, and SEN is a restriction to only translation rotation of EN, the group of isometries of Euclidean space. You don't have to know that. Yes, so same thing that I was saying for special Euclidean group, special orthogonal group. The special Euclidean group is a topological space and can also have a manifold structure. Same thing, so you can see that you can differentiate between like translating, rotating at the same time. The key idea of, so I didn't talk about this here, but the key idea is that these are associated with homogeneous coordinates, which is representing the position and adding a 1 to the coordinate of the vector. And this allows, so these are used all over the place because they allow to compute what is called forward kinematics. By multiplying positions using these matrices, you directly rotate and translate the vector. And you can chain these elements of SEN together, so usually SE3. So you can chain them by multiplying these matrices together. This would chain translations and rotations one after the other. So yeah, so for computer graphics, super important. For robotics, super important. Okay. So I will not go over the summary, I will just jump to the, I can need to read it here. Okay. All right. So we only have half an hour or less for today's lecture. So this new chapter is about matrix decompositions and what is the key idea? So the intuition. Well, so first, matrices are found all over the place in intelligent systems. So they are, as I said, so translations and rotations are represented by matrices, so elements of SC, or actually SC2. SC2 is for the car, because the car is translating and rotating on the plane. And camera images are matrices, so that should be clear, right? So this is actually only grayscale images are matrices. Pedestrian trajectories can be represented by matrices. So you can imagine that these guys here are specified by their coordinates on the plane, and then these change over time. The coordinates on the plane are going to be two-dimensional, maybe even three, because there's like a heading dimension to it. Maybe there's even another state component, like what is the activity? Is it like looking at his phone? Is it, things like that might be part of the trajectory. So you have like a state, and then over time, that's going to be a matrix as well. Of course, you can have a vector if you want. I said that multiple times, I think, during the lecture. You can, if you have a matrix, you can stack the columns of the matrix into a vector. And that's the basic idea of why matrices are actually vector space elements. Then that actually comes up like in when you actually implement stuff. If you have a trajectory and you want to, let's say, optimize the trajectory, you will make a vector representation, and then you can linearly transform that trajectory by multiplying that trajectory by a matrix. And that transformation matrix is going to optimize your trajectory. So that really comes up. And then the pedestrian data set is going to be a stack of these vectors. So you can vectorize a trajectory, as I mentioned. So you have kind of intuitive matrix representation of a trajectory. You can vectorize that, and then you can have a bunch of those in a data set. And this would be that. Okay, so we have our typical unit for machine learning, which is a data set, our typical unit for, let's say, computer vision or prediction of any kind, which is a trajectory and camera images, and then for robotics, a kind of like this, these matrices. So all over the place in intelligent systems, you'll find matrices as kind of the unit piece of data that you're working with. So we use matrices also to represent linear mappings. So we've just seen one, like the rotation matrix, how we have our linear transform between R2, and how we could convert that linear transform into a coordinate representation, which is this tiny rotation matrix. So you can do that for translations, for scaling, for stretching, for things. We also saw how we can use matrices to represent orthogonal projections, but also rotations and reflections, and a fine transform. This was at the end of the lecture. So as I said, data sets are often represented by n matrices, where m is going to be the number of instances that you have in your data set. So this is what we have here. So you have k of these pedestrian trajectories, and you want to learn a predictive model based on this data set of how humans move. This is like a typical problem in autonomous driving. N is the number of features that you're considering. So m is the number of rows, so the number of instances, and then n is going to be the number of features that you're considering for your problem. This is like the very kind of textbook way of representing data sets. Anyway, so to summarize or simplify matrices, we can use similar ideas as factorizing numbers. So if I have 21, I can get the factorized version of 21, which is 7 times 3, and I have my 2 prime numbers here that represent 21. So I have simpler elements, prime numbers, that represent 21. So that key idea of being able to decompose matrices into the product of simpler matrices, and then that might lead to much better numerically stable algorithms, might lead to a better understanding of what the matrix is. So we saw in the introduction lecture that we could apply the SVD to the data matrix. And this would lead to identifying what are the components of the data which have the highest variance, and then, this was PCA, so principal component analysis. So this is heavily based on the singular value decomposition, which we will see at the end of the lecture, but not today. Yeah, so the first thing when talking about matrices in detail is to really understand the key things about the matrix, so the determinant, the trace, and the eigenvalues. Really understand what they are, what they mean. How many of you guys know how to extract the eigenvalues from a matrix, from a squared matrix? You too. You're from Spain, yeah? Italy, okay. All right, so yeah. So we're gonna see that. We're not gonna go super deep into that, but we're gonna see like the basic, how to do that basically. And once you have the eigenvalues, you can get the eigen decomposition, which is a type of matrix decomposition, and then the singular value decomposition, which is generalizing kind of the eigen decomposition, because the eigen decomposition only works for squared matrices, whereas the singular value decomposition works for all matrices. Actually, the eigen decomposition doesn't even work for all squared matrices. So that's all. So I think we're only going to see the first section. This is only what I had in mind anyways. So the first thing is the determinant. Can someone tell me what they think the determinant represents? So what is it? Yeah, so it's like a scalar that's going to give us some kind of magnitude of the matrix. Yeah. But is it more related to the kind of like data view of what a matrix is, which is a bunch of vectors, or is it more related to the transformation view of like representing a linear transformation? I mean, we're going to see that anyways. But yeah, it's like a single number that helps to analyze the solution of systems of equations. So it's more related to like how the matrix represents a system of equations and how it's really kind of like transforming vectors. So it's defined for square matrices in this way. So it's a single number that we define this way, or we write this way with these straight lines here. So it will tell us when the matrix is invertible by saying, right, so let's first look at like the case where a matrix is a single scalar element. In this case, the matrix inverse is actually the reciprocal of the single number. And in the case of 2D matrices, what we get is this here. So what happens in inverting 2D matrices is that we swap the first diagonal, the elements of the first diagonal, and then we invert the sign of the second diagonal. And then we scale by this crazy stuff here. So that's the determinant in 2D. So it's we are multiplying the elements of this row here, and then we're subtracting the product of these elements here. And if the matrix is not invertible, if it's invertible, then the determinant is gonna be non-zero. And if it's not invertible, so we had a bunch of different names for not invertible. What did we say? So the matrix is singular. The matrix is, well, I don't know, there's a bunch of different names. Yeah, so the determinant would be 0. So the question is, how do we calculate the determinant? So I just explained that for the 2D case. For the 3D case, it starts to be more complicated. And the way we do that is called the Sarus rule here. So you can note that for an upper triangular matrix, which is squared, meaning a matrix for whose elements are all 0 if they're above the diagonal, the determinant is the product of the diagonal entries. It's the same thing if the lower triangle is 0. And that thing that a squared matrix is only invertible when the determinant is non-zero, that's actually a theorem. It's a determinant theorem. Okay, so we said that the determinant is some kind of magnitude of a matrix. So let's see how we can interpret that in terms of geometry. Let's look at the 2D case. So in the 2D case, we have defined our matrix this way. So we have A, D, A, B, C, A, B, C, D here. This corresponds to a parallelogram on the 2D plane where we have AB here and we have CD here. So we have the first vector is this vector here, and then the second vector is this vector here. Okay? So the determinant is the area defined by this guy, by the first vector, the first column here, and the second column here. So this is a parallelogram, and the area is given by this formula. This formula is also called, I think, the cross product, because what you're doing here is like you're doing this times this, and then you're making cross, so this times this. So that's for the 2D case. For the 3D case, what we have is we have 3 columns, and we have vector 1 here, vector 2 here, and vector 3 here. And then the determinant is going to be the volume of the parallelepiped defined here. That's just for the geometrical intuition. So it is the volume defined by the columns of the matrix in the sense of the volume of the parallelogram defined by these vectors in Rn. So equivalently to the Saros rule, we can define the Laplace expansion, which is a way to define the determinant, to calculate the determinant. And so this is a little bit tricky to see here, but the basic way how it works, so if we have an example here with a matrix, we first do, so we have two ways of doing it, so let's look at the row expansion way. This is the second formula here, basically saying that you compute the determinant here, then you compute the sub-determinant here, and then you compute the determinant of this guy and this guy, and you multiply by the coefficients on top, and the sign is going to change based on this rule here. So it's going to be plus, minus, plus. So what we get is this thing. Turns out that actually this matrix is singular. So we can do similarly the column expansion, which is going to have the same rule for the sign. If I didn't mess it up, maybe I did. I hope I got the sign thing right, because it looks kind of strange. Because here there's a minus. Okay, so that's just how to compute the determinant in the general case. So properties of the determinant. So the determinant of the identity is just 1. The determinant of the product of matrices is the product of the determinant. The determinant of the transpose is the determinant of the original matrix. The determinant of the inverse is the reciprocal of the determinant. That's only the case, of course, for non-singular matrices. The scaled determinant is the scale by the power of the size of the matrix of the determinant. And similar matrices, so we're going to talk about similarity a lot in this chapter. Similar matrices have the same determinant. That means that for a linear mapping from the vector space to itself, because it's a squared matrix, right? All transformation matrices have the same determinant. So it doesn't matter the basis in which the transformation matrix is defined, it will have the same determinant. If the determinant is non-zero, then the rank of the matrix is exactly the size of the matrix, so the number of rows or columns. Yeah, and that's it. So, yeah. Today I wanted to go back a little bit to this matrix representation of linear maps. So in matrix factorization and decomposition, it's very important to get that often we are talking about linear maps. We are reasoning on the coordinates of a linear map, so the matrix represents a linear map. So we have to understand how these coordinates arise. So generally linear maps, we define linear maps by just the linear property. So we have two vector spaces and we have a map phi, and we are just saying if we apply the map to two scaled added vectors, then this is equivalent to having the map applied to the first vector and scaling that, plus apply the map to the second vector and scaling that. That's linearity. So we define linear maps in this way. This is what linear maps are, and that's it. That's the end of what the coordinate-free version of linear maps are. Now, they can be represented by matrices, and this is what I'm going to talk about now. So if we have a linear map between a vector space V and a vector space W, where each of these vector spaces are associated with a basis, B, and C for W, then the transformation matrix associated with that linear map writes in the following way. So we have each of the column vectors of that matrix is defined by the coordinates of the basis vectors of the original vector space, so V, in the basis for W. So in the case of these rotation matrices, we said, okay, we are in R2 and we are mapping to R2 and we're looking at the same basis, E1, E1. We're just looking at the rotated mapped vector, the coordinates of the rotated vectors, E1 and E2, but with respect to themselves, E1 and E2. In the general case, we are looking at, so the columns of the transformation matrix are going to be the coordinates of the transformed vector in the output base, in the basis of the codomain, and not in the basis of the domain. That means that the coefficients, so the columns of the transformation matrix are the coordinates of the transformed vector in that basis. So these alpha here, these are the columns. So once we have this transformation matrix, the coordinates x hat and y hat. So x is an element of V and y is an element of W. Can be converted one into the other by multiplying x hat by the transformation matrix. But this doesn't answer why this is the case here, and this is what I wanted to talk about today, briefly. So if we consider basis vectors C and B for W and V, so remember, W is the codomain, and V is the domain of our linear map. So we can, what is this thing doing here? Okay, so if we have a linear map defined this way, we can define the map in the following way, in coordinates, by saying that y is a combination of the basis vectors of W, of our codomain basis vectors, which are called Ci. And now that's the tricky part. The so the coordinates of phi of x are going to be defined by what are the coordinates of x in the domain basis, which is the sum of the scaled basis vectors B, transformed by these maps that I called phi I C, which is giving as output the coordinate vector, well, the scalar associated with the basis vector Ci after transformation of x. Now, okay, so this is just like we're just defining stuff here. Now, we can apply the only property that we know this map phi respects, which is the linearity property. And we get this. We get that we can take out the scalars, the coordinates of vector x out of the linear transform by linearity, and we're just left with the transformation of the basis vector b. And now we can identify, okay, so now what happens here is that this summation that we have over J here. So we took that summation from the scalars out of V. And that summation that we have for J here, we put it into matrix form. So each of those here is actually a scalar. It's telling us what is the scalar associated with the ith coordinate, ith vector, basis vector of the codomain. And this is for vector, basis vector 1 all the way through n. And then we multiply that by the coordinate vector, which is just like stacking all these vectors, all these scalars together. Okay? So this is an inner product, right? So this is, or a dot product, sorry. This is a dot product between the vector xb and then the stack of all these maps here. So this is just how it's written here. And so now we can do the same thing for the outer summation here. So instead of having a sum of these dot products, what we do is we have a matrix form. We put them all into rows, and then we will multiply them by x here. Okay? And this is our transformation matrix. So this result is actually super important because matrices come up over and over. Transformation matrices of linear maps come up over and over and over again. So it's very important to nail down that what's happening is that we have the coordinates of the basis vector of the domains expressed by the transformation matrix. And the only trick that we do is just applying linearity here. I mean, this is just a bunch of like putting things together, like identifying that there are dot products here and there and putting this in matrix form. The real trick happens here, which is saying, so we have the expression of a vector as the linear combination of its basis vectors. We can just pull that thing out of the linear map. That's all. Okay, so the last thing is saying that if we're now considering the case where we have two ordered bases for the same vector space, then similarly, we can define a transformation matrix which is called S, which is operating a basis change. So it's a squared matrix, and it's a transformation matrix, just in the same way. But it's transforming, it's actually the identity matrix, but expressed in different coordinate systems. So in basis B tilde and in basis B, and we say that matrix is operating a basis change. Now, similarity is defined by having two matrices that are related in this way. And when we have this relationship between A and B, we say that A and B are similar. I think I talked about this already, but just this to two matrices here are said similar if there exists a non-singular matrix S, which with the following relationship. So yeah, so this is super important, this notion of similarity between matrices and the fact that S is actually just operating a basis change, because we're going to decompose matrices in three a lot when we do eigen decomposition and when we do singular value decomposition. And the key idea of decomposing matrices in three is often to say, okay, so we have on this side, we have some kind of basis change. On here for the eigen and singular value decomposition, we're going to have some kind of diagonal matrix, and then we are changing the matrix back into the other coordinate system. Actually, maybe reversely. So this coordinate, diagonal, this coordinate. And then this means a matrix will be called diagonalizable if it's similar to a diagonal matrix. And diagonal matrix, so are matrices that are super sparse, so they're full of zeros, and they just have coefficients on the diagonal. And they are extremely, we can do a lot of things with diagonal matrices. We can basically identify the eigenvalues, we can do all sorts of stuff. And yeah, so you should really be clear about what similar matrices are. Okay, so I think I wanted to reach the end of that, but I think we're out of time. So before the end of the section, there was quite some stuff. Okay, so I take it from the definition of trace next time. Okay. Thank you.